In this video, you're going to see a team working on a reverse engineering project from end to end. Different softwares and hardwares are going to be used along the way. Enovia, CATIA, and Simulia are going to be used on 3DEXPERIENCE in order to govern the project, re-engineer the parts, and validate it with simulation. The Cryoform HandyScan Black Scanner will be used to digitize the part at the beginning of the process. Finally, the MetalX printer by Markforged is going to be used in order to 3D print the new re-engineered part. Our company specializes in re-engineering OEM parts that have been identified as point of failures in subassemblies. By re-engineering those components, we offer our customers the opportunity to replace only the failing part instead of the entire assembly. Our aftermarket parts help them to save money. In the video that you will now be watching, the team is working on redesigning the impeller of a water pump. Since several engineers will be involved in the process, our company will use Enovia 3DEXPERIENCE project management application to collaborate. Different tasks will be assigned to the different engineers who will be notified when it's their turn to work. The first step of the process will be to scan the OEM part in order to get an STL file. Once this is done, the STL file will be handed to the CATIA engineer who will reverse engineer the part and create our new aftermarket impeller. The part will then be validated by our simulation engineer who will be in charge of checking that our impeller is better than the OEM one. Finally, the impeller CAD design will be validated and released using a digital workflow before being sent to 3D printing. The first thing that the project manager does when he logs onto 3DEXPERIENCE is to create a new project that will oversee the work of our different stakeholders. There are different ways to create a project. You can either start from scratch or create from an existing template. In that case, we will use the template that our organization has defined for reverse engineering projects. The project manager is now adding a picture to illustrate the project and adding a title and a description. As you can see, the project is now being created. It comes with a couple tasks that are coming from the template. Let's take a look at these tasks and do a couple modifications. The impeller part being very simple, the digitization is going to go very quickly. So, as an example, instead of the 1-day duration that was defined in the template, the project manager is going to change this task duration to about 2 hours. As you can see, the project Gantt chart is adjusting accordingly. Re-engineering the part will take a bit longer, so we will not change the duration here, and the same goes for the part analysis task. Finally, the releasing process should not take more than 3 hours. The project manager will now give access to this project to different persons. They will be given project member credentials first, and then be assigned to the tasks. So we will have Bart, our CAD engineer, Frank, the scan engineer, and Binod in charge of the part analysis and simulation. The next step is to assign them to their tasks so they get notified when it's their turn to work. Part digitization is assigned to Frank. When this is done, a description is added with instructions to perform the task, such as where to find the part to scan and its references. The re-engineering is going to be done using CATIA 3DEXPERIENCE. Bart, our CATIA designer, is assigned to this task. The simulation analysis is going to be done by Binod, who is added to his task. And finally, the release of the part will be initiated by the project manager himself. We will see how we can kick off a release validation workflow. Now that the project has been created and our tasks have been assigned, we're going to see the different assignees performing their work. What's going to be particularly interesting here is going to be to see how the data will flow from one user to the other thanks to the task dependencies and the different deliverables that will be attached. The first engineer who will be working on the project is the scanner engineer, Frank. Let's see him in action.
Hi, my name is Frank. I'm with the digitization group here at our company. My role is to 3D scan legacy parts as I'm assigned by our project manager, and in support of some reverse engineering that we do of suitable replacement parts for legacy products. The one thing that's unique about our company is that not only do we make replacement parts for legacy products, in our case we specialize in pumps, but many times we know what the mode of failure was of the OEM part. And a legacy product that's been in the field for maybe 2, 3, 5 years, the OEM may not be re-engineering or improving legacy parts anymore. So that's really where we fit in the market, is not only can we offer suitable replacement parts for legacy products, but we can also understand the mode of failure of those legacy products. And when we go through the reverse engineering process, we can improve those products. So my day starts on the 3DEXPERIENCE platform here by Dassault Systems. I come in, I log in every day, and I can see what my tasks are assigned for today. I can see if there's anything that's overdue. I can see any upcoming tasks for tomorrow or maybe later this week. In order to understand what I'm being asked to do for today, I just go in and open up the task, and I can see that I'm being asked to digitize a part, and here's some description of the part, the OEM, the make, the model, the year, and so on. It even tells me, our project manager was kind enough to tell me where I can find the part. It's in warehouse H on shelf 101. It's tied to this project, and here's the start date and finish date. He even was attached some pictures of the part so that I can be sure that when I go to the warehouse, I picked out the right part. So we're set up and ready to scan the part now. The scanner that we're going to use is a Creaform HandyScan Black, it's called. These are brand new. The nice thing that we like about these scanners is that they're totally portable. They plug into the USB port of a computer, and the portability, it weighs about as much as a hairdryer. It's very portable. I can get into the tight spaces if I wanted to scan something underneath the dashboard of a car, or in an armrest of a car, or a cup holder, or virtually anything. In our example here with the impeller, I've set up a little fixture, and you can see it's kind of a turntable type thing. I've got dots on the fixture. These dots are called targets. The scanner uses the targets to understand where it is in 3D space. We've got some 3D printed artifacts that we printed on our Markforged carbon fiber composite printer, and I just put some of the targets, these are stickers, that we set on the part, so I can kind of orient those randomly anywhere. The part, you notice that there are no targets on the part, so I don't need to have targets on the part to get an accurate scan, is really kind of the message here. And I just take the part, I set it down on the fixture. I offset the scanner by about 1 foot from the fixture, and everything's controlled off of the thumb controls here on the scanner. When I hit the thumb control, it starts scanning the part. We'll zoom in here a little bit so that you can see a little bit better what we're doing. That should be good. So we've got the part. Pretty much is the scanning process is fairly dynamic, so pretty much as quickly as I can, orient the scanner and rotate the turntable, you can see that it's picking up geometry, it's picking up data on the part. And as I said, we're going to do this on the top of the part, then we're going to repeat the process on the bottom of the part. Now you may be asking yourself, that looks great, but do I have to meticulously get every square micron of the surface area of the part? And the answer is no. What we want is we want a majority of the geometry on the part, but if I'm missing some geometry, does that really matter? No, because what I'm looking for is basically primary features, planes. I've got a hole through the middle of the part here, so I want to create a cylinder through that hole. in CAD, and we're going to recreate it. So now I've been scanning for about a minute. We'll go ahead and we'll pause the scanner here, and we'll show you some of the downstream cleanup applications. The software that we're running comes incorporated with the scanner. It's called VX Elements. Okay, so here we are back in VX Elements. Now what I'm going to do, I hit the space bar on the computer to kind of pause or suspend from the scanning process. This allows me to edit or clean up the scan as I need to. And what I really want to do is I want to get these artifacts out of the way because they're not needed. So I'm going to go ahead in the software. Allows me to edit the scan data. So I'm going to say select all of the elements that are connected to my part. And then if I inverse that selection, so I say select all the elements not connected to my part, and if I just hit the delete key on the computer and hit OK, now what happens is it deletes those other components from my part. So now I can go ahead and hit File, Save As, and I'm going to flip the part upside down, and I'm going to repeat this process in scanning the bottom. So now I've scanned the bottom of the part, and I've got the top of the part. I've merged the top and the bottom. And you can see I've got the part pretty well covered. I don't have 100% of the data. I had a couple of gaps, but the part is pretty clean and pretty complete. Now what I do is in the 3DEXPERIENCE platform, they want the deliverables attached to the workflow, to the process here. So I'm simply going to say go ahead and browse to the STL. Here's the STL file. You can see that's about not quite 6.5 megs in terms of size. And I'm going to say go ahead and attach that, and I'm going to tell it to save that along with this step in the process. So once I complete uploading the STL file, then I'm going to tell it that I've completed that task, and you'll see that it removes that task from my 3DEXPERIENCE dashboard of tasks to complete today. And now the next person in the workflow or in the process has been notified that they've got new scan data that's ready for reverse engineering in CATIA.
Now that the part has been scanned and its corresponding STL file has been attached as a deliverable to the task, we're going to see how Bart can use it in order to re-engineer the part in CATIA 3DEXPERIENCE. Bart, the CATIA 3DEXPERIENCE designer, just got notified that a task that belongs to the impeller reverse engineering project is assigned to him and ready to be worked on. After having quickly looked at the summary of the project, Bart opens the task section that is currently filtered on the tasks that are assigned to him. Bart can easily open the task and look at the work that is required.
Hello, my name is Bart, and I will be performing the reverse engineering of our impeller scan in CATIA 3DEXPERIENCE. Let's start by opening CATIA 3DEXPERIENCE, specifically the Digitized Shape Preparation app. The STL file, which is output from the scanner, can be imported into the platform within the Digitized Shape Preparation app. Next, we create the mesh in CATIA that will be used as the basis of the geometry creation. After switching to the Digitized Shape to Surface app, planar cross-sections of the mesh are created with automated tools in this workbench. Next, CATIA will convert those planar cross-sections into curves that can be used for CAD feature creation. The curves can be automatically smoothed as well. With our curves prepared, now we can create a simple revolve of the overall shape. With a CAD solid to work with, now we will use CATIA's Digitized Shape to Surface workbench to obtain primitive shapes that are mathematically approximated based on the mesh. These entities can include planes, cylinders, cones, and spheres, to name a few. Using the primitive shapes and construction elements that we have created, we will now split the existing solid into a proper base that we can build our remaining features on. This is all being done in the part design workbench, but could certainly be performed in a number of different workbenches within CATIA 3D Experience. Once the geometry creation is complete, we can overlay the reverse engineered model, the original scan, or any other legacy CAD data. A quick and simple deviation analysis shows if our part is within tolerance or not. With the deviation analysis completed, we can now switch to the virtual to real shape morphing workbench in CATIA 3D Experience. Shape morphing in CATIA allows the user to optimize and filter displacement vectors that are created within the deviation analysis. Once optimized, we can then use digitized morphing in CATIA to morph the entire solid towards or away from the target shape, in this case, the scan.
Bart has now completed the re-engineering of the part. In order to let the team know that he completed his work, he is going to open his task and promote it to the completed maturity state. Thanks to the project task dependencies, Binod just got notified that his task is now ready to be worked on. Let's see how Binod will be able to open the part, mesh it, apply loads, and run the simulation.
I got project in the project planner. I open the project. In tasks, I bring my tasks from today to in work. I open my task, analyze the part. I read the description, loading and requirement. Then I open the part, add as part in app, structural model creation. Then the part will open in native app. The part is open in model assembly. Once we initialize the final element, it will open in structural model creation. Then there I select the part, a component which I want to utilize in the analysis. I go to the mesh module. In the mesh module, I create a surface mesh with it with a triangular element. Then I use the tetrahedron filler mesh to fill that surface mesh. After the mesh is created, I go to model again. Then I assign a solid section for that solid element mesh, and then I assign a material. I look for 316 stainless steel, which is under the steel ductile. I scroll down till 316 stainless steel material. Once I found that material, I will select that and look for the material properties and click OK to assign it. After that, I'll update the model. Then I save the model. After my finite element model, the structural model is saved, I will open the model in mechanical scenario creation. I'll perform the structural analysis case. In procedure, I'll select the static state. I'll change the initial increment, and I will change it to be geometrically linear. After that, I will assign the restraint. For that, I'll choose clamp, and I will clamp the cylindrical part there. Then I'll go to loading. In the loading, I will select centrifugal force. I will apply centrifugal force to the whole model, and my axis of rotation will be the axis of that cylinder part. I will apply the rotational velocity of 10,000 RPM over here. After that, I will apply a pressure load on the two surfaces, on the face of the impeller, 100 psi pressure, and on the face of the wheel of the impeller. I'll select all those four faces which will where the pressure is applied to rotate the impeller. I'll click OK. I'll apply same amount of pressure, 100 psi here. After that, I'll go to simulate. I'll check the I'll make a model and scenario check. Check is completed. Then I go to simulate. Here the simulation is completed successfully, and this is the plot for the iterations per increments. Then here we'll see the von Mises stress, and the von Mises stress, let's change it to the engineering. It is 31,000, which is less than the 37,000 psi endurance limit for this material. So the design is passes for the stress requirement.
In this next section, we're going to see the project manager initiating the release workflow for the impeller part. In order to release the newly engineered impeller parts, he is going to start an engineering release workflow using a change action object. After having entered some basic information about the release workflow, such as giving it a title and a due date, the project manager is now assigning the work that needs to be done. The person in charge of validating that the part is ready to be released is going to be Roman. So Roman is added as an assignee and an approver. In the informed user section, Barton and Binot are going to be added. They will receive email notification when the process will move forward. The project manager will now add content in the proposed change section of the release workflow. The CAD data created by our CAD designer is going to be first frozen in order to prevent any further modification to be done on the data. Now that the data is frozen, it can be added to the release workflow. As you can see, the change action understands that those parts have been added to be released. As a referential, the physics simulation results are added. Roman, who is in charge of approving and releasing the data, will be able to access those simulation results in order to understand if the part has been designed within tolerances. Now that our work has been released, the new impeller is ready to be sent to manufacturing for 3D printing. A new STL file has been generated by the CAD engineer and assigned to Frank through a task. Frank will now show us how this STL file can be post-processed and sent to the printer.
At our company, we have implemented a 3D printing solution by an organization by the name of Mark Forged. We specialize in distributed manufacturing. So in our company, everything is accessible via the browser here. I can see that I've got printer assets in Cleveland. I've got assets in Florida and California as well. So I can send print jobs to available printers most close to the point of use or the customer as it's appropriate for my application. So I start my day within the 3DEXPERIENCE platform by Dassault Systems, and I can see a snapshot of what I'm being asked to do today. I can see a snapshot of maybe requests that are overdue or coming up tomorrow. In this simple example, I've got one request to 3D print a re-engineered impeller. So if I open up the request, I can see that I'm being asked to create a 3D printed part. They want it out of metal. Specifically, they want it out of stainless steel metal, and they want me to print a strong part, so they want maximum floors and walls. And I'm being asked to print a quantity of 1. The next thing that I'm going to do is I'm going to upload the part to our 3D printing environment. It's something called Eiger. So I'm going to go into my library, and I'm going to go into my customer folder. In this example, it's Acme Manufacturing. I'll say that I want to import the STL file. So I'm provided an STL by our engineers, and I've downloaded it into my downloads folder. So here's my impeller re-engineered. If I say open that and import the part, it comes into our system kind of looking like this. So I know that I've got a units problem. I'll change it to imperial units, and I'll scroll way out on the part so that you can see it. So the grid here is our build platform on this particular printer. I'm going to select the printing resource that I want. So I'm going to say that I want that out of stainless steel because that's what the request was. I'm going to sinter it in an oven. We're going to use a Sinter 2 oven. The settings for this, I'm going to take pretty much the default settings at this point, and I'm going to say that I want the infill to be maximum roof and floor layers and maximum walls, which is what the request said. So once I have all of those settings set, then I want to orient the part on the print bed. In my example, I'm going to say that I want to orient the part on that bottom. If I want it on the top, I just pick a surface and it flips the part accordingly. So here I've got my, my part pretty well set, and I'm going to say save that. Now this software can run locally. It can run via web browser access, which is what we run here. And again, by virtue of running it on a web browser, allows me to see all of the 3D printing hardware and assets that I have available to me across the country. So what the software is doing now is it's actually creating the toolpath. For those of you that are familiar with NC processes, this is just like creating the G-code to run the 3D printer. By virtue of doing this, I'm creating, it's going to tell me how long it's going to take to print. It's going to tell me what the material cost is. My next step then is to create the print file, and I'm going to push that to the printer, and I'm going to attach the print file to the 3DEXPERIENCE platform. So I can see that my material cost is $48.01. I'm going to say go ahead and print that. So it orients it on the print table. If I wanted to add multiple parts here, I could do that. If I zoom out, I can see you know, the physical printer. It's going to create a raft for the part as well as the appropriate supports, so I don't have to do the work to calculate that. What I want to do then is I'm going to export the build into a download. So it's going to create a executable print file that I'm going to store on the 3DEXPERIENCE platform as a record, so that we know in the future, here's the actual print file that created that physical part. When I say export build, it creates the file for me and it downloads it as a native print file that cannot be modified by me or anybody else. So again, this is my file of record that once we've produced this part, this is the physical file that produced that specific part.
In terms of key takeaways, it's important to mention the ease of use. As you could see, all those different users with different roles in the organization were using the same platform, and even though they were using different applications, the user interface was always the same. Having a project governing the workflow from scanning the part to releasing it and sending it to 3D printing helped to break the silos and increase collaboration. Everyone in the project were able to access the different deliverables. This gave more visibility on the work that was being done, and the digital workflows were improving work traceability.